Your last blood test probably missed something. Not because your doctor made an error, but because the test wasn't designed to find it. The standard markers most physicians rely on can look completely normal for years, while a deeper metabolic shift is already underway, quietly changing how your body handles the food you eat every single day. The subject is carbohydrates, but not in the way you've heard before. The debate that has dominated nutrition for 50 years, low-carb versus high-carb, good carbs versus bad carbs, the food pyramid versus keto, was never really about carbohydrates. It was about the wrong question, asked repeatedly, by people who were certain they had the right answer. And the people caught in the middle, trying to do the right thing, following the guidelines, switching to whole grains, cutting back on sugar. Many of them are still watching their numbers move in the wrong direction. Not because they failed, because the map they were given was drawn for someone else's body. What the research actually shows is more specific and more actionable than any version of this conversation you've encountered. It involves what happens to your metabolism after 50 inches weighs. Most physicians never explain. It involves bacteria in your gut making decisions about your blood sugar that no diet book has ever accounted for. And it involves changes you can make starting at your next meal, not by eliminating anything, but by understanding something. What was the dietary advice that quietly misled millions of careful eaters for 30 years? Why does the same meal produce dramatically different results in different bodies? And what do the small daily choices you make at the kitchen table have to do with how clearly you think a decade from now? There's a good chance you've been lied to about carbohydrates. Not maliciously, not by anyone with a clear agenda, but lied to nonetheless through oversimplification, through headlines designed to sell books, and through a scientific debate that got hijacked somewhere between a Senate hearing in 1977 and the low-carb revolution of the early 2000s. The result is a generation of health-conscious people over 50 who are trying to make intelligent decisions about food using a map that was drawn for someone else's body, at a different moment in nutritional science, with a different set of questions in mind. Here is where it started. In the late 1970s, the US government released dietary guidelines that placed fat, particularly saturated fat, at the center of the heart disease epidemic. Carbohydrates, by contrast, were positioned as the safe alternative. The food pyramid was built on that foundation, and an entire industry reorganized itself around it. Fat came out of products. Sugar and refined starch went in to replace the flavor. And for roughly 2 decades, Americans followed the advice faithfully, because it came from authoritative sources and seemed to make biological sense. The results were not what anyone hoped for. Obesity rates climbed. Type 2 diabetes cases multiplied. And eventually a backlash formed loud, confident, and almost as incomplete as the idea it was replacing. The news story became, carbohydrates are the real villain. Fat was innocent all along. Cut the carbs, fix the metabolism, reverse the damage. Atkins. South Beach. Eventually, keto. Each wave more certain than the last. Each one treating the previous consensus as naive and the new framework as finally correct. What both sides shared, and this is the part that almost never gets said out loud, was a fundamental habit of treating carbohydrates as a single thing. As if a bowl of lentils and a can of soda belong to the same biological category, simply because they both contain glucose molecules. As if the body of a 28-year-old athlete and the body of a 58-year-old with years of metabolic wear behind him would process the same plate of rice in the same way and arrive at the same outcome. The category existed. The biological reality did not match it. That gap between the label and what actually happens inside a body is where the hidden truth lives. And for people over 50, it's not an abstract distinction. It's the central fact that should be shaping every conversation about diet, and largely isn't. Because after 50, the body's relationship with carbohydrates has already shifted in ways that most people haven't been told about, can't feel in any obvious way, and therefore cannot respond to intelligently. Research published through the NIH has documented this trajectory in detail, showing that metabolic changes in how the body handles glucose begin well before any clinical diagnosis appears quietly, invisibly, in the background of what feels like normal health. The question worth asking now isn't whether carbs are good or bad. That question has been answered, poorly, too many times already. The better question is, what is your body actually doing with the carbohydrates you eat, and what has changed about that process since you turned 50? Because the answer to that question is more specific, more actionable, and more surprising than anything the good carb, bad carb debate has ever produced. That answer starts with something most people have never been clearly told about their own metabolism. A shift that begins silently, registers too late on standard tests, and by the time anyone notices it, has typically been underway for a decade. Sometime in your late 40s or early 50s, something changed in your metabolism. It didn't announce itself. There was no symptom you could point to, no morning you woke up feeling categorically different. It happened gradually, in the space between cells, in the language of hormones and receptors that the body never translates into anything you can feel directly. And by the time most people become aware that something has shifted, the process has typically been running for years, sometimes for a decade or more. It's called insulin resistance, and for adults over 50, it is arguably the single most important metabolic development to understand because it quietly changes the rules for how carbohydrates behave inside the body, rules that most people are still playing by the old version of. Here's the mechanism, explained without jargon. When you eat a carbohydrate, any carbohydrate, your digestive system breaks it down into glucose, which enters the bloodstream. Your pancreas detects the rise and releases insulin, a hormone whose job is to act like a key, unlocking the doors of your cells so glucose can enter and be used for energy. In a metabolically healthy body, this system is efficient and responsive. The key fits. The doors open. Blood sugar rises, then falls back to baseline within a reasonable window of time. What changes with age, accelerated by inactivity, by chronic stress, by years of high glycemic eating, and by the natural hormonal shifts that accumulate after 50, is that the cells begin responding less reliably to insulin's signal. The key still works, but the locks have stiffened. The pancreas compensates by producing more insulin. Blood sugar still normalizes, eventually, but the process takes longer, requires more hormonal effort, and leaves behind a metabolic environment that is persistently, quietly different from what it was 15 years ago. Research supported by the NIH and published in Frontiers in Endocrinology has made this trajectory explicit. Hyperinsulinemia and insulin resistance associated with aging are linked to elevated risk of neurodegenerative disease, cardiovascular disease, and type 2 diabetes, and centenarians, notably, tend to preserve significantly better insulin sensitivity than their peers, suggesting that this isn't an inevitable consequence of aging so much as a modifiable one. For people over 50, the practical consequence of this shift is that postprandial glucose, meaning blood sugar after eating, becomes far more relevant than fasting glucose for understanding what's actually happening metabolically. A body with developing insulin resistance can maintain perfectly normal fasting blood sugar while producing dramatically elevated spikes after meals. Those spikes, repeated multiple times a day over years, are what accumulate into risk. Risk for cardiovascular damage, risk for cognitive decline, risk for the slow progression from insulin resistance into full type 2 diabetes. And yet fasting glucose is what gets checked at most routine appointments, because it's simple, inexpensive, and has been the standard for decades. By the time it flags a problem, the underlying resistance has often been building for years. This is where carbohydrates re-enter the story, not as villains, but as variables. Because if postprandial glucose is the real issue, then the type of carbohydrate, the quantity eaten in a single sitting, the speed at which it digests, and what it's eaten alongside all become genuinely consequential, not in the abstract, not as nutritional theory, but as levers that directly affect how high that blood sugar spike goes and how long it stays elevated. A 55-year-old eating instant oatmeal with orange juice for breakfast isn't making a choice that looks bad on paper. Both foods carry healthy reputations, and by simple nutritional logic, the meal seems reasonable. But for a body with developing insulin resistance, that combination rapidly digested carbohydrates, no fat, no protein to slow absorption, taken in the morning, when cortisol is already pushing glucose higher, can produce a postprandial spike that a 30-year-old eating the same meal would barely register. That's not a reason to fear breakfast. It's a reason to understand what's happening and to make choices with that understanding in hand. Which brings us to the tool that was supposed to solve exactly this problem. A tool built on a genuinely good idea, used by millions of health-conscious people, that contained a flaw significant enough to quietly mislead an entire generation of careful eaters. In 1981, a researcher at the University of Toronto named David Jenkins published a paper that should have changed the way everyone thought about carbohydrates. In many ways, it did. But the version of his idea that reached the public simplified, flattened, repeated until it hardened into conventional wisdom, lost something essential in translation. And that loss has been quietly misleading health-conscious people for more than 40 years, including people who considered themselves well-informed precisely because they knew about it. Jenkins developed the glycemic index. The concept was elegant in its original form. Instead of categorizing carbohydrates by chemical structure alone, why not measure how quickly each food actually raises blood sugar compared to a reference point, typically pure glucose? Foods that spike blood sugar rapidly received a high number. Foods that caused a slower, more gradual rise received a low number. It was a genuine improvement over simply dividing foods into simple and complex carbohydrates, and assuming that distinction captured everything that mattered. For the first time, there was a tool that tried to measure biological impact rather than just chemical composition. The problem wasn't the index itself. The problem was what happened when people began using it as a standalone guide, as if a single number assigned to a food in a laboratory setting, measured in isolation, consumed by a fasting volunteer, could reliably predict what that food would do inside a real person eating a real meal in the real world. Consider watermelon. On the glycemic index, watermelon scores around 72, a high number, sitting in the same range as white bread. For years, this made watermelon a food that nutrition-conscious people approached with genuine suspicion. A fruit with vitamins, antioxidants, and a water content above 90%, quietly placed on the caution list because of a number that was measuring the wrong thing. What the glycemic index captures is the speed of blood sugar response per gram of digestible carbohydrate, but it says nothing about how many grams of digestible carbohydrate are actually present in a realistic portion. Watermelon has a high glycemic index because its carbohydrates digest quickly. A typical serving, however, contains so little total carbohydrate that the actual blood sugar impact is modest. The index measured how fast the car accelerates. It said nothing about how much fuel was in the tank. That's where glycemic load enters the conversation, and why it matters so much more for practical decision-making. Glycemic load combines the glycemic index with the actual carbohydrate content of a realistic portion, producing a number that reflects real-world blood sugar impact with far greater accuracy. Watermelon's glycemic load per standard serving sits around 4 on a scale where anything below 10 is considered low impact. White bread, which carries both a high glycemic index and substantial carbohydrate content per slice, produces a glycemic load that reflects both of those facts simultaneously. Harvard Medical School researchers have published extensively on this distinction, consistently showing that dietary patterns built around low glycemic load, not merely low glycemic index, are associated with meaningfully reduced risk of type 2 diabetes and cardiovascular disease in middle-aged and older adults. The mechanism is straightforward. It's not just how fast glucose arrives that determines how hard the pancreas has to work, but how much of it arrives at once. For someone over 50 navigating insulin resistance, this distinction isn't academic. It's the difference between avoiding an entire category of genuinely nutritious foods based on a flawed metric and understanding that portion size, food combination, and context can shift a meal's glycemic impact substantially without requiring the elimination of anything. A person who abandoned watermelon, carrots, or beets because of their glycemic index scores was making a sacrifice that the science never actually asked for. But here is what even glycemic load doesn't capture, and this is where the research has moved in directions that most people haven't heard about yet. Even two people eating identical foods in identical portions with identical glycemic load on paper can have metabolic responses that diverge in ways that are not small or marginal. The reason for that divergence lives somewhere most nutrition conversations still barely visit, inside an ecosystem so complex that some researchers have begun calling it a separate organ entirely. There are approximately 38 trillion microorganisms living in your gut right now. Bacteria, primarily, but also fungi, viruses, and archaea. An ecosystem so complex and so metabolically active that some researchers have begun calling it a separate organ. And over the last 15 years, the science investigating what that ecosystem does has quietly rewritten several assumptions about nutrition that most people still carry as settled fact. One of those assumptions is that two people eating identical meals will experience broadly similar metabolic responses, assuming similar age and body composition. It seems reasonable. It turns out to be wrong in ways that matter enormously for anyone trying to make intelligent decisions about what to eat after 50. The evidence came into sharp focus through research at the Weizmann Institute of Science, later expanded in a study published in Diabetes Therapy that tracked 550 adults consuming more than 30,000 meals collectively. The findings generated serious attention across the scientific community and serious discomfort for anyone invested in the idea that general dietary guidelines could work uniformly across different bodies. Glycemic responses to identical foods varied dramatically between individuals, and a significant portion of that variation was explained not by the food itself, but by the composition and activity of each person's gut microbiome. Some participants spiked sharply after foods considered metabolically safe. Others barely responded to foods that conventional wisdom would flag as problematic. The foods weren't the constant, the bacteria were the variable. What the gut microbiome does with carbohydrates, particularly complex carbohydrates and dietary fiber, is fundamentally a fermentation process. Certain bacterial species break down carbohydrates the human digestive system cannot process on its own, producing short-chain fatty acids in the process. These compounds, particularly one called butyrate, have effects that extend well beyond digestion. They influence the integrity of the intestinal lining, modulate systemic inflammation, affect insulin sensitivity at the cellular level, and interact with the nervous system in ways researchers are still mapping. A microbiome rich in these bacterial species extracts more nutritional value from complex carbohydrates while generating less inflammatory noise. A depleted microbiome compromised by years of low-fiber eating, repeated antibiotic use, chronic stress, or consistently poor sleep tends to process the same foods with considerably more metabolic consequence. For adults over 50, this matters for a reason that rarely gets stated plainly. Microbiome diversity tends to narrow with age, not inevitably, but as a consequence of habits that accumulate over decades. Less dietary variety, more processed food, more medications, more sustained stress. Each of these factors individually reduces the range of bacterial species present, and most people over 50 have experienced several of them in combination over many years. A narrower microbiome is a less metabolically flexible one. It produces fewer of the short-chain fatty acids that support insulin sensitivity and intestinal integrity, and generates more of the inflammatory byproducts increasingly associated with metabolic aging and cognitive decline. The practical implication is one that almost never surfaces in nutrition conversations. If your microbiome is depleted, you may be getting a substantially worse metabolic outcome from foods that should, in theory, be working in your favor. Whole grains that a diverse microbiome would ferment efficiently, producing butyrate, supporting insulin sensitivity. Dampening inflammation may pass through a compromised gut, with far less benefit and more inflammatory residue. The food didn't fail you. The ecosystem that was supposed to process it has been running understaffed for years, quietly, without anyone telling you. The genuinely good news is that the gut microbiome is among the most responsive systems in the human body. It reacts to dietary changes faster than almost any other biological marker. Measurable shifts in microbiome composition occur within 48 to 72 hours of changing dietary fiber intake, not months, days. The bacterial species that thrive on fermentable fiber grow when fermentable fiber is consistently present, and their return has cascading effects on glucose regulation, inflammation, and metabolic resilience. Which brings us to the nutrient sitting at the center of this entire story, the one the science treats as foundational infrastructure, and most people still treat as an afterthought. Ask most people what they know about fiber, and you'll get a version of the same answer. It keeps you regular. It might help with cholesterol. You should probably eat more of it. Then the conversation moves on, because fiber doesn't have the drama of omega-3s, or the cultural momentum of probiotics, or the clean narrative arc of intermittent fasting. It has been filed, somewhere in the collective health consciousness, under things that are fine but not particularly interesting. That filing is a mistake, and the science makes the case more forcefully than almost any other area of nutrition research. Dietary fiber is not a single substance. It's a broad category of plant-based carbohydrates that share one defining characteristic. The human digestive system cannot break them down into glucose. They pass through the small intestine largely intact and arrive in the colon, where the gut microbiome takes over. What happens there has consequences that reach far beyond digestion. An umbrella review examining 31 independent meta-analyses found that individuals consuming the highest amounts of dietary fiber showed statistically significant reductions in cardiovascular disease mortality, coronary heart disease, and stroke risk, with risk reductions ranging from 9 to 28%, depending on the outcome measured. That's not a marginal finding. That's a consistent signal replicated across decades of research and millions of participants. The American Heart Association endorses a total dietary fiber intake of 25 to 30 grams per day from whole foods specifically to maximize cholesterol-lowering impact. The mechanism is precise. Soluble fiber forms a gel-like substance in the digestive tract that binds to bile acids made from cholesterol, forcing the body to draw on its cholesterol reserves to produce new bile acids and effectively pulling LDL out of circulation. Compounded over years, alongside other dietary factors, it represents meaningful and well-documented cardiovascular protection. But the cardiovascular story is almost the least surprising part of what fiber does. And this is where the conversation usually stops short of what matters most for people over 50. Soluble fiber slows gastric emptying, which directly reduces the speed at which glucose enters the bloodstream after a meal. The same carbohydrate eaten with fiber versus without it can produce a substantially different postprandial curve. Same calories, same total carbohydrate content, fundamentally different metabolic trajectory. The American Diabetes Association has incorporated this into its current nutritional guidelines, specifically recommending high-fiber carbohydrate sources for blood sugar management in adults with or at risk for type 2 diabetes. The recommendation isn't tentative. It reflects decades of consistent clinical evidence pointing in the same direction. Then there is the inflammatory dimension, which connects directly to what the previous block established about the microbiome. Insoluble fiber feeds the bacterial species that produce butyrate and other short-chain fatty acids, which have a direct anti-inflammatory effect on the intestinal lining and dampen the low-grade systemic inflammation increasingly associated with metabolic aging and cognitive decline. These aren't separate benefits running in parallel. They are interconnected mechanisms: cardiovascular, glycemic, microbial, inflammatory, all activated by the same dietary input, operating simultaneously, compounding over time. The average American currently consumes between 10 and 15 grams of fiber per day, against a recommendation of 25 to 38 grams. That gap is not a minor shortfall to be addressed gradually. For someone over 50, managing developing insulin resistance, reduced microbiome diversity, and early inflammatory burden, closing it is one of the highest priority dietary interventions available and consistently the one least likely to appear in a headline. What the next block reveals is why that gap carries consequences that extend further than most people expect, all the way to how clearly you think at 70. And what is happening inside the brain right now to determine that? There is a question that neuroscientists have been circling for roughly 2 decades, one that has moved from the edges of academic speculation toward something approaching clinical consensus. The question is this: to what degree is cognitive decline the gradual erosion of memory, processing speed, and executive function that many people over 50 begin to notice and quietly fear, driven not by inevitable neurological aging, but by metabolic dysfunction that has been accumulating in the background for years? The answer, increasingly, is more than most people realize. The brain is the most metabolically demanding organ in the human body. It accounts for roughly 2% of body weight and consumes approximately 20% of the body's total energy, almost entirely in the form of glucose. That dependence makes the brain exquisitely sensitive to disruptions in glucose metabolism and particularly sensitive to the kind of chronic, low-grade dysregulation that develops alongside insulin resistance in adults over 50. Here is the mechanism researchers have been documenting with growing precision. In a brain affected by insulin resistance, and yes, insulin resistance can develop in brain tissue independently of what's happening elsewhere in the body. Neurons begin to struggle with glucose uptake. The insulin signaling pathways that normally facilitate energy delivery to brain cells become less responsive. The cells don't starve outright, but they operate under a kind of chronic energy insufficiency that impairs their function, accelerates inflammation, and over time affects the structural integrity of neural connections. Some researchers have begun using the informal term type 3 diabetes to describe this pattern of brain insulin resistance observed in Alzheimer's patients. It remains a working hypothesis, not an established diagnostic category, but the underlying observation that insulin resistance in the brain tracks closely with amyloid accumulation, neuroinflammation, and cognitive decline has been replicated across multiple independent research groups and taken seriously enough to reshape how some neurologists think about dementia prevention. The most compelling population-level evidence connecting dietary quality to cognitive outcomes comes from Rush University Medical Center and Harvard, where researchers developed the MIND diet, a hybrid of the Mediterranean and DASH dietary patterns, specifically designed to target brain health. In a landmark 2015 study published in Alzheimer's and Dementia, participants in the top third of MIND diet adherents showed a rate of cognitive decline equivalent to being 7.5 years younger in chronological age compared to those in the lowest third, not slightly younger. 7.5 years. The foods emphasized by the MIND diet, leafy greens, berries, legumes, whole grains, nuts are, without exception, foods that stabilize blood sugar, support microbiome diversity, and reduce systemic inflammation. It is, at its core, a carbohydrate quality story expressed in the language of cognitive neuroscience. What this means practically is that the postprandial glucose spikes, discussed in earlier, the ones occurring multiple times daily in a body with insulin resistance, that most people cannot feel and therefore do not prioritize, are not only a cardiovascular or metabolic concern. Each spike triggers an inflammatory response. Each inflammatory response, repeated with sufficient frequency over sufficient time, contributes to a biological environment in which brain tissue is more vulnerable and less resilient. The connection between what you eat at breakfast and how clearly you think at 75 is not metaphorical. It is biological, documented, and increasingly difficult to dismiss. None of this means that optimizing carbohydrate quality guarantees cognitive longevity. Genetics matter. Sleep matters. Physical activity matters enormously. But it does mean that what happens at your kitchen table 3 times a day is participating in a biological conversation that reaches all the way to your brain. A conversation that was happening whether you knew about it or not. And there is another part of this story that connects those kitchen table decisions to something that happens hours later, while you are asleep, through a mechanism almost no one has ever connected to their carbohydrate choices. Most people think about what they eat in terms of what happens immediately afterward, the energy they feel or don't feel, the fullness that lasts or fades too quickly. Very few think about what their last meal is doing at 2 a.m. when they're unconscious and have no awareness of any process whatsoever. But something is happening. And for a significant number of adults over 50, what's happening at 2 a.m. is quietly undermining the benefits of everything they're trying to do during the day. The connection between carbohydrates, cortisol, and sleep quality is one of the most underappreciated loops in metabolic health, and understanding it requires following 3 threads simultaneously. The first thread is cortisol. Cortisol is the body's primary stress hormone, produced in a rhythm fundamentally tied to the sleep-wake cycle. Under normal conditions, cortisol is lowest in the early hours of sleep, begins rising in the pre-dawn hours, and peaks shortly after waking, preparing the body for the demands of the day. This rhythm is ancient, conserved across mammals, and deeply important for metabolic regulation. Because cortisol, among its many functions, raises blood glucose by signaling the liver to release stored glucose into the bloodstream. The second thread is what high glycemic eating does to this system. When blood sugar spikes sharply after a meal, particularly an evening meal high in rapidly digestible carbohydrates, the subsequent crash can trigger a counter-regulatory response. The body, detecting falling blood glucose, activates the stress response. Cortisol rises. This can happen in the middle of the night, producing a physiological state that is the opposite of restful sleep, elevated stress hormones, mild glucose fluctuation, and a nervous system nudged toward arousal rather than deep recovery. The person may not fully wake. They may simply cycle out of restorative slow-wave sleep into lighter stages, repeatedly, without ever understanding why they feel unrefreshed in the morning despite spending 8 hours in bed. Research funded by the NIH and the National Institute of Diabetes and Digestive and Kidney Diseases has made the bidirectional nature of this relationship explicit. A study examining the effects of mild but chronic sleep restriction, just 1.5 hours less per night, found significant increases in insulin resistance in women across all age groups, with effects that were independent of changes in body weight and reversed once normal sleep was restored. The mechanism runs in both directions. Poor sleep worsens insulin sensitivity, and poor glucose regulation disrupts sleep architecture. Once the cycle begins, it tends to tighten rather than resolve on its own. The third thread is what aging specifically does to this dynamic. After 50, slow-wave sleep, the deepest, most physically restorative stage, naturally decreases in duration. The body becomes more sensitive to disruptions, including the mild nocturnal glucose fluctuations that a younger metabolism might handle without consequence. Research published in the American Journal of Clinical Nutrition, using data from the Women's Health Initiative, found that a high glycemic index dietary pattern was associated with significantly increased risk of insomnia symptoms, with the proposed mechanism being exactly the one described here. Postprandial glucose fluctuation triggering counter-regulatory hormonal responses that fragment sleep continuity. What this means practically is that the timing and composition of evening meals carry consequences that extend well beyond digestion. A dinner heavy in refined carbohydrates eaten within 2 to 3 hours of sleep doesn't just affect blood sugar during digestion. It sets in motion a hormonal sequence that can fragment sleep architecture, elevate overnight cortisol, and leave the body in a subtly more stressed and less recovered state by morning. Repeated nightly, this pattern contributes to the cumulative metabolic toll that accelerates aging in ways that feel inevitable, but are, in significant part, dietary. The intervention isn't dramatic. More fiber, more protein, alongside carbohydrates at dinner, attention to timing. Small adjustments with consequences that compound nightly, across months and years, into meaningfully better recovery and a metabolism better equipped for what comes the following day. If you've been paying attention to nutrition for any length of time, you've absorbed a rule that feels solid and sensible. Choose complex carbohydrates over simple ones. Whole grains over refined grains. Brown rice over white. Oatmeal over sugary cereal. The logic is clean, the advice is everywhere, and it has the virtue of being directionally correct better than nothing, better than the alternative it replaced, and genuinely useful as a starting point. The problem is that most people stopped there, treating complex carbohydrate as a destination rather than the beginning of a more precise conversation. Consider brown rice versus white rice. Brown rice retains its bran and germ layers, providing more fiber, more magnesium, more B vitamins, and a modestly lower glycemic index. All of that is real. But its glycemic index still sits in the moderate to high range, and eaten in typical American portion sizes without significant protein or fat alongside it, it still produces a meaningful postprandial glucose response for a body with developing insulin resistance. Better than white rice? Yes. A metabolically neutral food? No. Whole wheat bread presents a more counterintuitive version of the same problem. Whole wheat kernels eaten intact have a cellular structure that slows digestion significantly. The fiber is physically encased in a matrix. The digestive system has to work to break down. But commercial whole wheat bread is made from whole wheat flour, meaning the grain has been milled into fine particles, destroying that protective matrix entirely. The result is a food with a glycemic index remarkably close to white bread, often within 5 to 10 points, that most people treat as categorically different. The bran and germ are technically present. The structural advantage is largely gone. Oatmeal is genuinely different and worth understanding precisely because it illustrates what the distinction should actually look like. Steel-cut oats retain enough structural integrity that digestion slows meaningfully. The beta-glucan fiber in oats forms a viscous gel in the digestive tract that blunts glucose absorption and has demonstrated consistent LDL-lowering effects in clinical trials. Steel-cut oats have a lower glycemic index than rolled oats, which have a lower glycemic index than instant oats, not because the nutritional composition differs dramatically, but because the degree of processing determines how much structural integrity remains. This is the variable the simple, complex versus simple framework misses entirely. There is also a concept worth introducing here that most people have never encountered: One that David Jenkins, the same researcher who developed the glycemic index, first described decades ago, and that has been accumulating supporting evidence ever since. It's called the second meal effect. What you eat at breakfast influences your blood sugar response at lunch, even when lunch is eaten 4 to 5 hours later and contains identical foods on every occasion. A breakfast high in soluble fiber produces fermentation byproducts in the gut that persist into the afternoon, moderating glucose absorption at the subsequent meal. Studies measuring this effect have found postprandial glucose reductions at lunch of 20 to 30%, simply as a consequence of what was eaten at breakfast, with no change to the lunch itself. You're more than halfway through this video, and what's coming next is the part most people never connect to this conversation. Subscribe before you forget, and send this to someone who needs it. They'll understand why when they get here. Now, the second meal effect is only one dimension of a broader principle that the final block of this video is going to make fully concrete. Context transforms carbohydrates. And the most actionable piece of that context, the one that requires no elimination, no calorie counting, and no special foods, involves something as simple as the order in which food arrives on your fork. Research conducted at Weill Cornell Medicine put a number on something most people have never thought to measure. Participants consumed the same meal on separate occasions, changing only the sequence in which they ate its components. When protein and vegetables were eaten first, followed by carbohydrates, postprandial glucose peaks dropped by more than 28% compared to eating carbohydrates first. A subsequent study in participants with prediabetes found reductions exceeding 40% using the same approach. The total food consumed was identical. The calories were identical. The only variable was the order in which the food arrived in the digestive tract, and that order changed the metabolic outcome dramatically. The mechanism involves gastric emptying and incretin hormone release. Protein and fiber consumed first slow the rate at which the stomach releases its contents into the small intestine, and simultaneously trigger hormonal signals that prepare the body to handle incoming glucose more efficiently. By the time the carbohydrate portion arrives, the digestive environment has already shifted in ways that blunt the glucose curve. This isn't a marginal effect found in a single small study. It has been replicated, published in Diabetes Care, the Journal of the American Diabetes Association, and is now the basis of a behavioral intervention being tested in pre-diabetic populations across multiple clinical sites. Macronutrient pairing works through the same underlying logic. Fat and protein consumed alongside carbohydrates slow gastric emptying regardless of sequence, which is why an apple eaten with a handful of almonds produces a slower glucose response than an apple eaten alone. The apple didn't change. The digestive environment it entered changed. For adults over 50, applying this consistently, never eating significant quantities of carbohydrates in isolation, always pairing them with protein, fat, or both, the cumulative effect across a day, a week, a year, is genuinely substantial. No food eliminated, no calories counted, just context, applied deliberately. Then there is physical activity timing. Muscle contraction increases glucose uptake independently of insulin through a separate pathway that remains functional even in insulin-resistant tissue. A 10 to 15-minute walk taken within 30 to 60 minutes after a carbohydrate-containing meal channels circulating glucose directly into working muscles before insulin resistance has a chance to produce a prolonged spike. The American Diabetes Association has incorporated post-meal physical activity into its current lifestyle recommendations, precisely because the evidence is consistent and the barrier is as low as it gets. It doesn't require a gym. It doesn't require intensity. It requires movement, timed deliberately. After eating, think about the people you know who seem to age differently than their peers, who carry less metabolic wear, who think more clearly, who move through their 60s and 70s with a kind of biological ease that looks almost unfair from the outside. They are not, as a group, people who followed stricter rules or eliminated more foods. They are people whose daily habits, whether consciously or not, happened to align with the mechanisms this video has been tracing from the beginning. The fiber was there. The pairing was there. The movement after meals was there. The carbohydrates were present, understood, and used well. That is the thing the 50-year debate never said plainly. Not that carbohydrates are safe, not that carbohydrates are dangerous, but that carbohydrates, like almost everything else in biology, are only as consequential as the context surrounding them, and that context, it turns out, is almost entirely within your control. If this conversation changed something, subscribe, share it with someone who needs it, and tell us in the comments what you want us to go deeper on next. That's how this continues.